For this episode of the Physics Chalkboard, we'll take a closer look at how to solve vector problems, using one of the best and fastest methods for tackling them clearly and confidently. The sample problem we're using in this walkthrough is taken from the textbook Sears and Zemansky's University Physics with Modern Physics by Young and Freedman, 13th edition, specifically from page 18. This book is an excellent resource for anyone studying physics at the university level, and I highly recommend checking it out if you're looking for detailed explanations, derivations, and a wide range of practice problems. So let's begin. You may pause this video now to take a moment and read through the problem statement. In simple terms, the problem asks us to solve for the resultant of three given vectors. Now, whenever you're given more than two vectors, the easiest and most logical way to solve them is by using a free body diagram in combination with the component method. A free body diagram is a simplified illustration where you isolate and sketch each vector individually. This is especially practical because you don't need to worry about the relative scale or proportion of one vector to another. You're simply focused on direction and labeling. It helps you visualize the problem more clearly before moving on to the mathematical steps. Let's begin with the given information. Always remember, not all givens are numbers. In many physics problems, the problem illustration is just as important as the numerical values. That's why your free body diagrams, FBDs, are considered part of the given. They help you visualize direction, orientation, and relationships between vectors. Let's begin by illustrating the free body diagram, FBD, of vector A. Vector A is located in the first quadrant because its direction is described as 32 degrees east of north. This means the angle is measured starting from the northward, positive y-axis, and then turning 32 degrees toward the east, positive x. Since the vector lies in the first quadrant, it's practical to limit your diagram to that region. Focus your axes and workspace in the upper right quadrant to keep things neat and clear. Don't forget to draw vector A as an arrow. Direction is crucial in vector representation. The arrow helps you clearly see where the vector is pointing, which is essential for identifying its components. Now, because vector A is going both east and north, we can conclude the following. The horizontal component, A sub x, points to the right, positive x-axis. The vertical component, A sub y, points upward, positive y-axis. This directional breakdown will help us set up the component equations correctly when we move on to solving. Let's move on to representing the components of vector A using mathematical equations. It's time to put your trigonometry hats on. If you look closely at your free body diagram, you'll notice that you formed a right triangle. And when there's a right triangle, our best friend in solving for sides is the classic mnemonic, SOHCAH2A. Let's break that down quickly. Sine equals opposite divided by hypotenuse. Cosine equals adjacent divided by hypotenuse. Tangent equals opposite divided by adjacent. In this case, take a look at A sub x. It lies opposite the 32-degree reference angle. The hypotenuse of the triangle is the magnitude of vector A itself. Applying SOH, we use sine to relate the opposite side and the hypotenuse. And there you have it, the horizontal component of vector A in equation form. We'll keep it that way for now. Let's now move on to finding the equation for A sub y, the vertical component of vector A. Notice that A sub y is adjacent to the 32-degree reference angle we're using. Together with the hypotenuse, which is the magnitude of vector A, we now have another right triangle relationship. This time, the appropriate trigonometric function is cosine, since cosine relates the adjacent side to the hypotenuse. So we write, cosine 32 degrees is equal to adjacent side, A sub y, divided by the hypotenuse, A. That gives us the equation for the vertical component of vector A. Again, we're just setting up the structure for now. We'll plug in actual values later when we work through the full solution. Let's now move on to the free body diagram, FBD, of vector B. Vector B is located in the third quadrant because its direction is given as 36 degrees south of west. This tells us that the angle starts from the westward, negative x-axis, and turns 36 degrees downward toward the south. So, just like before, we'll focus our diagram on the relevant space, in this case, the lower left quadrant. Following the same process as we did with vector A, we'll resolve vector B into its horizontal and vertical components. You may pause or replay this section if you need more time to follow how we build and label the equations. Important reminders. Vector B is moving to the left, negative x direction, and downward, negative y direction. This means that both b sub x and b sub y will have negative values in your final component table. The FBD of vector is C can be quickly illustrated because it lies in the y-axis going south. This readily gives us the insight that c sub x is 0, while c sub y is simply c in the negative direction. Now that we've resolved all three vectors into their x and y components, it's time to get their totals. But before we jump into the computation, let's take a moment to understand the logic behind this step. Why do we resolve vectors into components and then combine all the x components and all the y components? To help visualize this, let's use a PhET simulation. Watch as we pull three vectors onto the screen. Notice how each vector has both horizontal and vertical parts, and look closely at what's happening. The horizontal components align along the x-axis, while the vertical components stack up along the y-axis. This is exactly what we do in vector addition. We're collecting and summing all x components together and all y components together. This way, we reduce multiple vectors into a single combined vector with a net x and net y direction. Keep in mind, some of these components are negative, depending on direction, so always refer to your illustrations or free body diagrams to get the signs right. Now let's write the summation equations to gather all x components, indicated here as summation of x and summation of y. Sum of vectors in the x is equal to a sub x, positive because it is eastward, plus b sub x, negative because it is westward, plus c sub x, which is 0. Substituting all values in this equation gives us a value that is negative. The negative does not mean anything else other than it is westward or toward the left. Next, let's write the equation for the summation of y. Sum of vectors in the y is equal to a sub y, positive because it is upward, plus b sub y, negative because it is downward, plus c sub y, which is vector c itself. Substituting all values in this equation gives us a value that is positive. So what does the summation of components actually suggest? Let's go back to our PhET simulation to help illustrate this idea more clearly. There's a button here labeled Sum. Go ahead and click that. Now pay close attention to the vectors that appear in dark blue. The vector along the x-axis represents the total horizontal component. The vector along the y-axis shows the total vertical component. These two vectors, sum of x and sum of y, form the legs of a right triangle. From here, we can trace a hypotenuse between them, and that hypotenuse is our resultant vector. Using the Pythagorean theorem, we can now solve for the magnitude of the resultant. The horizontal sum is negative, so the vector points to the left. The vertical sum is positive, so it points upward. If we now close the triangle by connecting these two components, we create a right triangle, and the resultant vector is the hypotenuse. This visual clearly shows the overall direction of the resultant, and from here, it becomes a matter of solving the triangle mathematically. Important tip: even if one or both component values are negative, your triangle itself contains only lengths, not signs. So when solving, just use the absolute values of your sides. The direction is already taken care of in your diagram. To find the magnitude of the resultant vector, we apply the Pythagorean theorem. Next is the direction. Let's label it as theta. To find theta, notice that opposite to it is the sum of y, while adjacent to it is the sum of x. This brings us an equation that states the tangent of theta is equal to opposite side, sum of y, divided by adjacent side, sum of x. This angle gives us the direction inside the triangle. From here, you can express the angle depending on what form is required. If your teacher asks for a polar angle, simply inspect the triangle and subtract your reference angle from 180 degrees if it lies in the second quadrant. If using cardinal directions such as bearings, you may describe it as an angle west of north or similar. So there you have it. We found the magnitude of the resultant to be 12.7 meters, and the direction is either 129 degrees in standard polar form or 39 degrees west of north using compass bearings. And that wraps up this problem-solving walkthrough here on the Physics Chalkboard. We've broken down the vector problem step by step. from drawing free body diagrams, resolving components, summing vectors, and finally finding the magnitude and direction of the resultant. Remember, mastering vectors takes both visual logic and mathematical fluency, so don't be afraid to pause, rewind, and try the steps yourself. The more you practice, the more natural it becomes. If you found this helpful, give the video a thumbs up, and don't forget to subscribe for more physics walkthroughs and concept breakdowns. Join me next time as we tackle more physics challenges made simple, visual, and clear. Until then, keep learning, keep questioning, and keep chalking out those answers. And this has been the Physics Chalkboard.